Hi everyone, can you please confirm if I'm audible? Okay, just let me know. Just let me know if I'm audible, right? So that we can just start. Okay, great. So let's just get started. So I think I'm audible, right? So we are going to start with the part two of the discussion. So let's just start with the questions in the AIMT2 that we have asked. Okay, so let's just get started. Now let's just see this question. What this question is saying: consider the scenario where L is shared variable, right? So am I audible or there's some disturbance? Like there's some background disturbance, or am I audible clearly? Can you just confirm? Okay. So this question is saying, let's just see this question. What this question is saying? This question is saying that we have one shared variable which is L, which means that this is synchronization problem, and we are dealing with the race condition most probably, right? Now they are saying that there are two threads T1 and T2 which are using this shared variable L. Now this L is a shared variable which is basically pointing. So L is a variable of this particular type, right? Struct type. I mean, which is pointing to a linked list basically, right? The head of the linked list. So this is the linked list, and L is a pointer. L is a pointer which is pointing to the linked list. Okay. Now, what else they say? They are saying that the linked list originally contains 3, 4, 5. So initially, let's suppose it contains 3, 4, 5. So 3, 4, and then let's suppose it contains 5 also. Okay. Great. Now they are saying that assume T1 invokes list insert 2 and concurrently thread 2T invokes list insert 6. So basically, they are saying that T1 is a thread which wants to insert 2, and if you see this code, it is actually inserting at the front, right? It is creating a new node, okay, in the heap, which means using the malloc, and then it is saying new key equal to key, which means it will be 2 if it is the thread 1, and then new next equal to L. Then what does this mean? It means this is new, basically new is pointing here, right? New next is equal to L, which means whatever L is pointing to, this new next will start pointing to the same thing, right? Whatever L is pointing to. And now they are saying L equal to new. L equal to new means, see, new is pointing to this, so now L will start pointing to this. Now L will start pointing to this. So which means this code is basically being used. Actually, this code is being used by two of the threads concurrently. So what is the possible answers here? Can anyone tell me what are the possible answers here? See, this is the code, right? Now the possible answers, as you can notice, see, this is basically containing, I think, 3, 4, and 6. Sorry, 3, 4, and 5. So it is already containing 3, 4, and 5. And now you are saying that you are inserting 2, right? See, these are the three steps which are being executed concurrently. So you are creating a node, and then if let's suppose this is being executed by T1 and T2, right? So this is basically saying that this new, if you notice, this new is a local variable, right? So this is actually not a problem here, which means this new is a local variable. It's not dealing with the real race condition. So the till now, basically till now you are modifying just the local variable things, right? So till now there is no race condition. The only race condition which will arise is equal to L equal to new. So which means there is a new, okay, this is new, which will start pointing to this, and then this will be either having 2 or 6 depending on whether it is which thread is there, right? So it will be having, let's suppose, 2 or 6. Then this will start pointing here, and then till now there is no race condition. I mean, that's not an issue. Okay, but the moment you do L equal to new, then there might be the race condition. So basically what is happening here is that it may be possible that the threads are executing this code one after another, right? I mean, there is one scheduling by which they are executing one after another. So if they are executing one after another, then it may be possible that L basically has been modified to this, and then you are inserting 6 later on. So it may be possible that you are first inserting 2 and then 6, which means 6 to 3 4 5 is definitely possible. 6 to 3 4 5. What else is possible? Yeah, L is a head of linked list. It is given, right? L is a shared variable which is a pointer to head of a linked list originally containing 3 nodes, right? L is a head of linked list. Now this is definitely possible if 2 is being inserted and then 6 is being inserted, or maybe 6 is first being inserted and then 2 is being inserted, right? So this is definitely possible. This is possible, this is possible. Now the only interesting case is that is this possible that I'm losing one of this, I'm losing that, okay, I may not even insert 2. Is this possible? Let's just check. See, till now, till this particular point, there won't be any race condition, which means, as I told you, that this will basically say that, see, this new is pointing and so on, right? Okay. Now let's suppose two, like the thread which is inserting 2 is basically calling this particular function, and then till now let's suppose this thing is done. Now L equal to new, right? L equal to new means that L will start pointing to whatever it is pointing to. But now before this L equal to new, it may be possible that other thread is also doing the same thing, which means concurrently, maybe the other thread is also scheduled, and then other thread is saying that, okay, I have a different local variable which is new and which is pointing here. See, new is a local variable which is in the stack, and stack is not shared. Okay, stack of the thread is not shared. Okay, it is a different. So basically there are two new. Okay, for every of the thread there will be a different new, because new is basically the shared variable, the local variable, right? Now let's suppose both of the threads are till this point. Okay, are till this point. Now this L equal to new. Let's suppose that if this thread is executing L equal to new, then I mean first, then this L will start pointing here. Otherwise, L will start pointing here. So maybe you are losing one of this, right? Maybe you are losing either 2 or 6. So definitely 2, 3, 4, 5 is possible, and 6, 3, 4, 5 is also possible. Hence, all are possible. So you will say all are possible. 6, 3, 4, 5, 2, 3, 4, 5, or maybe 6, 2, 3, 4, 5, or 2, 6, 3, 4, 5. So this is a nice and easy question, I think, right? An easy question. Let me know how many of you were able to do and how many of you were not able to do this question. Let me know. How many of you were able to do? Okay, okay. So some of you are able to do, right? That's really great. Okay, that's really great. Didn't read the question. Okay, one user is saying that didn't read the question in the exam, thought it might be difficult. No, it is easy question. It was nice and easy question, right? It was easy question only. Cool. Now let's just move to the next question, which is this. This was also very nice question. Okay, this is a question where we are using round robin scheduling. Okay, we are using round robin scheduling with a quanta of 20 units. Now, interestingly, generally when we use round robin scheduling or any other scheduling, I mean, especially with the round robin scheduling in the questions, we see that there is no arrival time. I mean, we say that all the processes have been arrived simultaneously, but here we have the arrival times, right? Now let's just see that how we can solve this particular question. Okay, how we can solve this particular question. Sorry. So now let's just see that if you want to solve this particular question, then how you can approach this particular question. Here this question specifically deal with one of the very important concept. And what is that concept? This question deal with that how round robin basically behaves in case of the arrival times are different. So let me first tell you that how it will behave. Suppose you are scheduling. Okay, you are having round robin scheduler, right? So there is a queue. Let's suppose A, B, C have been arrived. Now let's suppose you will schedule A, you will schedule B. So the moment, see, whenever A is running, okay, the moment A is running, let's suppose A is running, okay, A has to run from here to here. Let's suppose A has to run from here to here. So the moment A is running, in that time, let's suppose in between D is coming. Okay. So there are two cases when the A is running, in between the D is coming. So see, A is not in the queue, but if D is coming in between, then D will be pushed like this. And let's have a different case. See, this is the case one where A is running and in between D is coming. So there are two cases I can say. Okay. This is a different case. So there are two cases. In between, if while A is running, in between if D is coming, okay, let's suppose here the D is coming, then D will be pushed here. But let's suppose that A is out, and then D. I mean after A, who will run? Tell me, who will run after A? B will start running, right? B will start running. So A is out, and then B has start already running, and then what we will do? We will push A. We will push A, and then since D is coming here, so we will push D here. So see what is the difference? That here once this A is out, then A will be pushed back, right? I mean, because that it's, let's suppose that its execution is not over. It need to be executed more. So basically here the order is BCDA. Here the order is BCAD. Okay, are you getting my point? See, I hope you are getting the difference, right? So basically, you need to maintain a queue, and whenever some process is coming in between, you put it at the end. Okay, you put it at the end, right? Now let's just solve this question. Let's just maintain a queue. Tell me who is there in the queue at first? Only A is there, right? Only A is there. A is there, and because the arrival time of A is 0. Now time count is 20 units. So basically, A will run for 20 units. A will run. You can say A will run for how much time? A will run for 20 units. So for 20, from 0 to 20, A will run, right? And now its execution time will remain to be 25. Now at 19, which means at this place, at 19, who is coming? B is coming, right? At 19, B is coming. So you will say that this B will get pushed because A is not in the queue. And now once this A is over at 20, A will again get pushed back, right? Okay, so at 20, this is the queue, right? This is the queue at 20. Now what you need to do? You just check that what else you need to do. Now this B, right? B is there. So you will say that, okay, let me run this B for 20 unit of time, but this is only 15. So I think B will run just for 15 unit of time. And then you will say that, okay, this B is over after 15, which means this is 35, right? So this B is now over. Now till 35, only A is there because C will come at 40. So only A is there. You will pop this A, and then you will say that, okay, this A is there, and then it will run for 20 more times. So which means it is till 55 it will run, right? Okay. What we need to zoom? I think this is visible, right? Because I need to have multiple things in the same slide. So I think this is visible. Okay. Okay. So now this till 55, you can say till 55 you have this C was there, right? I mean at 35 C was not there, but at the moment of 55 C will be coming. So C will be pushed, and then A will be still remaining. So you need to push A again. Okay, now at 55 you have C, so it need 20, but you will be running it for, you have C, you will be running it for only 20, so 10 will remain, right? So till 75 you will run this, and at 75 D is not still there, so that's fine. So A is there, so you will run the A remaining 80. So this is 75, remaining 80 you will run. At 80 D will come, so you will say this is fine. Now at 80 D will come. So D will come now, right? So which means you will say D is now here. At 80 D will come, which is fine, and I think this A was running, right? Now at 80 D will come, and then you will say that, okay, D need 50 unit of time. Okay, D need 50 unit of time. So you will be running it for some time, which is I think till 100 you will be running it, and then E will come. Okay, then E will come. So this is D. Now E will come, and then D will get pushed back. So it will be 30, right? It will be 30. Now D and E at 100, D and E both are having 30 and 30 only. Okay, D and E both are having 30 and 30 only. At 100, D and E both are having 30 and 30 only. Now can you use just round robin quickly? Okay, so after that you will be just running E, right? E for 20 unit of time, right? And then D for 20 unit of time, and then E for 10 unit of time, and then D for 10 unit of time, right? So basically it is, if it is 100, then this is 20 unit, 120, then 140, then 150, and then 160, right? Okay. So what they're asking is that in the Gen chart at 0, what is the time that E finishes the execution? So I think there is some calculation mistake we have done. I think E is finishing the execution at 160, right? So what is the calculation mistake we have done? Okay, this is 110 at 90 after 90. Okay, this is not 75 to 80 and 80 to 90. 75 to 80 and then 80 to 90 only we need to run C. Okay, C is remaining, right? Oh, C, I think the 10 unit of time we have not run C. Okay, so C is remaining. So 80 to 90 we have to run the C. Okay, I think 10 unit of time we have missed this C. So then 80 to 90 we will run this, and then basically this will be 110 and 90 to 110. Basically we need to run D. Okay. Anyway, like this will be 110, then this will be 130, this is 140, then this is 160. Okay, and then this is at last it will be 170. So basically yeah, see 10 seconds we forgot to execute. So anyway, basically you need to see that how to maintain the queue. Okay, let me know if you found this question interesting. Let me know. See, you need to maintain the queue to solve this question, right? Okay, you need to maintain the queue. So I hope that is fine, right? I hope that is fine. See, this queue is very nice. Like, I mean, in round robin, that how this queue is working, this particular concept is really needed here. How many of you were able to solve this particular question in the exam? This was little long question, I agree, little long, not that much long, but you need to see that how to maintain queue in round robin. Right? How to maintain queue in round robin. How many of you were able to solve this? Let me know. Okay. So now let's just solve this question. This question is saying what will be the output of the following program? See, here you have a character array, right? This is an array. So let me just go over the next page, and let me tell you that how to solve this particular question. Yeah, it was easy, but I mean the last question was easy, but round robin concept was really needed. So here you will say that there is an array of character pointers basically, which means there is an array, and let me just make the diagram here. There is an array, and basically this is the array of character pointers, which means it is pointing to some character, it is also pointing to some character, it is also pointing to some character. The character it is pointing is O, which happens to be a part of string, which is okay, which means orange. The character it is pointing is apple. The character it is pointing is pear, right? And now they are saying that you need to run this loop 2 times, which means for I equal to 0 and I equal to 1. And then what this is doing is saying that you are passing, this is str of 0 address of this, which means you are passing the address of this. This is the address of this is basically a double pointer, which means that now in this particular function, what this particular function is doing, s1 will be pointing here initially and s2 will be pointing here, right? S2 is also a double pointer, and s1 is also a double pointer, which points to something, which points to a character, right? So that's the hierarchy is. Okay, now they are saying that you are swapping which one, star s1, which means star s1 means this is s1 is this, star s1 means this particular thing and this particular thing. So basically you are basically exchanging, or you are swapping these two, which means at first instance you will be basically saying that okay, let me basically point here and let me point here. So after the first iteration of this loop, they will be pointing like this, right? And then you will be asking, see here, I think the diagram is here, this is the initial, and after the first iteration it will point here and it will point here. After the next iteration of the loop, then you will also swap these two, right? So if you swap these two, it means it will point here and it will point here. So this particular thing will not get changed, which means this particular thing will keep on pointing to apple. This particular thing will keep on pointing to apple, but this will keep on pointing to apple, but this will get point to orange, this will get point to pear. So this is the final diagram that you will be having. And now they are saying after this whole execution, what you need to do, you just need to print, right? So if you execute this, if you try printing it, then percentage s, which means str of 0 percentage s. So it means it is basically the address of the string, right? So str of 0 is apple, and then pear, and then orange. So apple, pear, and orange will get printed. Okay, easy but nice question. This was also nice question, I think. Okay, let me know if you have understood this. Okay, great. Now this question, let's just try to solve this question. What they are saying, that you need to find the value of g of g2, right, which are mutually recursive functions. So let's just see that how to find the value of g of g2. See here that this g of g2 is basically a basically, I mean, this is already calling this g2. So let's just first find out the value of g2. If you find out the value of g2, then it seems that you need to find out the value of g1 and f1. So let's just do one thing. Let's just make one array. Okay. I mean, just like a dynamic programming. This is, let's suppose, f. Okay. F of, let's suppose, 0, f of 1, f of 2. This is, let's suppose, g of 0, g of 1, and g of 2. Let's just find out these 6 values quickly. What is f of 0? Can anyone tell me? And what is g of 0? F of 0 is seeming to be 0, and g of 0 is seeming to be 1, right? Okay. So let's just fill this table. And then f of 1 will be f of 0 plus g of 0. So basically f of 1 will be a summation of these two. So f of 1 will be this. So it seems that f of 2 will be summation of these two, right? So let's just first find out g of 1. So what is this g of 1? G of 1 will be g of 0 and f of 1. So g of 0 and f of 1. So these two. So basically this is 2. And now you can sum this up, it will be 3. Then you can sum this up, it will be 5, isn't it? So basically you can see the pattern here. This is 0, 1, 3, and then this is 1. I mean, here you added 1, and then you added 3. Anyway, so basically what you are saying, that if you want to fill this, you can fill using these two, right? If you want to fill, let's suppose, something like this. If you want to fill this, then you can fill using this diagonal. Okay. So let me just tell you that what they are trying to say is something like this, right? Is something like this. So suppose this is f. Okay, 0, 1, 2, 3, 4, 5. Let's suppose I want to fill these values 0, 1, 2, 3, 4, 5. This is, let's suppose, for f, and similarly I want to fill all of these values for g also. So for f and g I want to fill all the values. So let's suppose this is f and this is g. Then initially this is 0 and this is 1, right? This is 0 and this is 1. Now what you need to do? You basically need to say that, okay, if you want to fill this, you can sum these two, which means it will be 1. If you want to fill this, you can sum these two, so it will be 2. If you want to fill this, you can sum these two. This is 3. If you want to fill this, you can sum these two. This is 5. If you want to fill this, you can sum these two. This is 8. If you want to fill this, you can sum these two. This is 13. If you want to fill this, you can sum these two. This is 21. If you want to fill this, you can sum these two, right? This will be 4 and 5, 54. If you want to fill this, you can sum these two, which means it will be 5, 7. If you want to fill this, you can sum these two, right? Okay. Is there any mistake, or everything is fine? Sorry, I think this is 4 and 3. This is 34. The sum of these two is 34. And then sum of these two will be 5 and 5, 55. And sum of these two will be 89, right? Will be 89. So let's suppose that I have filled the array like this. Okay, which means to fill this, I can sum these two, and then similarly to fill this, I can sum these two, right? Okay, I can sum these two. So now let's just see that what they are asking. G of g2, which means g of 2 is 5. So they are asking g of g2, and g of 2 is 5. So essentially they are asking g of 5, which is actually 89. So 89 is the correct answer here. Okay, 89 is the correct answer here. Let me know if you have understood this method. Okay, actually this is what you can say, the dynamic programming in practice. Okay, we are actually doing the dynamic programming. Okay, you can solve using this long method also. I mean, the thing is that here you need to maintain, okay, what was the g of 2, and okay, g of 2 is essentially being used here and so on, right? So this is basically the thing that you are having a repeated call, right? If you are having repeated call, then why not you use the dynamic programming in the real execution? Okay, so let me know if you have understood this method correctly. So this is basically the dynamic programming that you are using in the real world. Okay, dynamic programming. You can use the dynamic programming to solve this question. Okay, it is not like not like the case that only if they say that they use dynamic programming, then only you are using dynamic programming. You can use the dynamic programming even if they do not mention directly, right? So you can understand this question as a dynamic programming question, and then you can definitely solve like this. You can just see the pattern that okay, this is the summation of these two, this is summation of these two, and then solve this question, right? Great. Or otherwise you can definitely solve using this way. Okay. Now let's see this question. This is also very interesting question. This was also very interesting question. What this question is saying, that suppose there is an array, and let's suppose in this array you swap two elements, which is a of 5 and let's suppose a of 10. Okay, let's suppose a of 10 or something. Then okay, you're swapping two elements. This is a swap code. Then they are saying that the number of inversions, maximum number of inversions, can be eliminated using this. Okay, maximum number of inversions that can be eliminated. So let me first tell you something. Let's suppose this is your elements. Okay, let's suppose this is some array and you have two elements which are, let's suppose, this 110. Now for example, assume that this array basically, I mean, whatever element you put here, okay, this will see, these two elements are inverted already, because this is a reverse sorted, which means this is 100 and this is 10. Reverse sorted is actually the inversion. Now whatever element you put here, that may be the element greater than 10 and lesser than 100, maybe even greater than 100, maybe even lesser than 10. In all the cases it will be having the inversion with 10, so or 100. So what do I mean? Let's suppose case 1. Okay, case 1, the element that let's suppose you put here is 5. Case 2, element you put here is, let's suppose 50. Case 3, element you put here is, let's suppose, even greater than 100, right? 500. If you're putting 5 here, is this reverse sorted with this? Is this reverse sorted? No, but it is definitely reverse sorted with this. So it means that it is definitely reverse sorted with this. It means what? That this particular element is having the inversion with this, right? And if you put 50, then is it reverse sorted with 100? No, right? I mean, this is so reverse sorted means, yeah, this is reverse sorted with 100. Reverse sorted means that okay, this is higher number, this is lesser number, right? So yeah, this is basically having inversion with 100. It is not having inversion with 10, that is fine. But let's suppose you put 500, then it is increasing order. For 100 there is no problem, but for 10 there is a problem. So what I mean to say, in all of these cases, this 5 is having inversion with whom? This 100 and 5 is an inversion, right? This is inversion. Similarly, if you put 50 here, then you want, let's suppose you are increasing order, and then if you put 50 here, then this 100 and then 50. So this is decreasing, right? So 100 and 50, again inversion. And if you put 500, then 510, again inversion. So basically what I'm saying, whatever element you put in between any inversion. So if a pair is inverted, then whatever element you put, all the elements are inverted, right? All the elements are inverted either with this or with this, right? Is this okay to everyone? Let me know. Is this okay to everyone? Let me know. Okay. So now tell me, what are the worst case inversions that you have? Suppose there is an array. Okay. Do you know the worst case inversions? It is a reverse order, completely reverse order, right? Which is n into n minus 1 or plus 1 by 2, right? So this is, let's suppose 1, 2, 3. Let's suppose there is some array which is given to you. Now suppose this is 0, 1, 2, 3, 4, 5. Okay. Suppose this is A5, 6, 7, 8, 9, 10. This is A10. Okay, this is a5, this is a5, let's suppose this is a10. Okay, suppose, okay, suppose this is a5, this is a10. Now you tell me, what is the maximum number of inversions it can have? Any array, it will be in the reverse sorted fashion, which means maybe you can have some numbers here which are reverse sorted. Maybe you can say this is 100, this is 90, this is 80, this is 70, this is 60, this is 50, and so on, right? So basically, if you notice here, if you have some elements like this, okay, which is 100, and then 90, then 80, then 70, then 60, then 50, and so on. If you have something like this, okay, in that case, you basically say, see that this 100 is having inversion with everyone, right? This is having with 90, this is having with 80, this is having with 70, this is having with 60, this is having with 50. Similarly, this 90 is also having inversion with everyone, right? Similarly, this 80 is also having inversion with everyone. Okay. Similarly, this 70 is also having inversion with everyone. So this is the maximum number of inversions that you can have in any array. Now suppose you do one thing. You say that, okay, let me swap these two, okay, a5 and a10. Let's suppose these are a5 and a10, which means after swapping it will become 50 and it will become 100. Okay, after swapping, suppose that is the case. Then tell me, any inversion among this has been changed, or these are the same, which means 90 was already inverted with 80, 70. I mean the reverse sorting, which means decreasing order is inversion. Okay, decreasing order is inversion. So is this change or is this same? These inversions are same, right? Whatever inversions they have earlier, now also they are same, isn't it? The inversions might got have changed is basically the 100 was inverted with all of these elements, right? All of these elements. So these are 1, 2, 3, 4, 5 elements. So these are the 5 elements. The 100 was inverted. So now 100 is not inverted with any of this element, right? So basically the 5 inversions you are making less because of the 100. Okay, see, whatever is among them that you haven't changed, but this 100 was inverted with all of this. So you are saying that, okay, whatever the earlier inversion which are n, now it is n minus 5 because of 100. Similarly, this 50 was inverted with whom? 50 was having inversion with all of this, right? With 100 also, but I've already counted this 100. So 50 was having inversion with all of this, which is 4. So now does this 50 have inversion with any of this? No, right? So 50 also doesn't have any inversion. So basically 5 because of 100 and 4 because of 50. So basically you are making 9 less inversions. Okay. So you can say at most you can decrease by 9, which means at most this 100. Okay, at most this 100 maybe getting inverted with all of this, right? And now if you're changing the position of 100 to be here, then you are saying that, okay, now it will not be inverted. Now it will not be inverted with any of this. So basically the 5 inversions here you are making less, and this 50 is basically inverted with all of this, right? Including 100, but 100 will get over counted. So that's why I'm just saying this. Now 50 will not get inverted with any of this. Now whatever is the later element and whatever is the before element, actually the thing here is that these elements, according to these elements, we are not changing anything, right? I mean the positions of 100 and 50 is basically relatively the same. So before elements and later elements, we don't need to worry. We are not changing anything here. The relative positions we are not changing. The only thing we are saying that, okay, because I'm swapping this 50 and 100, then this 100 may be earlier be inverted with all of this, okay, with all of this. Similarly, this 50 may be inverted with all of this, okay. So that's why 9 inversions you are making less. Let me know if you have understood this. Okay, 100 because of 100, these are the 5 inversions. Because of 50 also 5 inversions, but one inversion which is 100 comma 50 will get counted twice. So 10 inversions total you are making less, but one inversion got counted twice. So 9 inversions is the answer. Is this understood? See, let's suppose earlier before that, you have, let's suppose, any number, okay, maybe you have 500, maybe you have 10 or any numbers, okay. Suppose you put this 100 anywhere after it, okay, anywhere after it, okay. I mean, as long as you are not entering into their area, you're shifting 100 anywhere. Tell me, with respect to this, anything is changing, okay? With respect to this, I mean, earlier this 500 was having inversion with 100 and 10 was not having. So if you even if even if you put the 100 anywhere here, with respect to this, nothing will change, right? Nothing will change. Similarly, as long as this 50, similarly for this 50, as long as you don't enter into their area, okay, don't enter into their area, as long as you shuffle them. So basically, this 50 was having the inversion with 500, but not with 10. So similarly for the 50 also, there is no change, okay. अमित इज सेइंग गलती से सही हो गया. हाँ, गेट में भी ऐसा होता है कि मतलब हम सोचते हैं कि ठीक है ये आंसर होगा तो हम कर देते हैं. Okay, but this was really a good question. See that whenever you are changing this 150 positions, whatever elements are before them, it doesn't matter. I mean, whatever you change them, the number of inversions with respect to them doesn't change. Similarly, after it, whatever the elements with respect to them, it won't change. So basically, the only change you will be having increasing or decreasing, okay. Whatever the earlier, because of this won't change. Let's suppose because of this there were x inversions, because of these there were y inversions. Even if you change them, even if you make this 50, make this 100, then there will be at least x plus y will be there, okay. I mean, the number of inversions won't change here, okay. So this, if this is, let's suppose these are the x inversions because of this, these are the y inversions because of this, then the number of inversions won't change because of these, right? Okay. So let me just ask you a question. Let's suppose there is an array, okay, given array of 100 elements. Let's suppose I'm having a 1 to 100, okay. I'm starting with 1. Suppose they are saying there are 10 inversions, or maybe let's suppose there are 20 inversions in sub array okay, in sub array a 1 to 50, with elements a 51 to 100, okay, 51 to 100. So basically let's suppose there are a 1 to 50 and then 51 to 100. I mean, there are basically, because of this 1 to 50, I mean these 1 to 50 are having 20 inversions with 51 to 100. I mean, with this these are having 20 inversions, let's suppose. Now suppose you are making any change in this 51 to 100, okay. Now suppose some change you are doing, we sort a 51 to 100, then number of inversions of a 1 to 50 with 51 to 100 will be how much? I mean, maybe the question language is very naive, but yeah, we can definitely well frame this question. But I hope you are getting my context here. What I'm trying to say, that earlier, let's suppose if these are the 100 elements, okay. Earlier, let's suppose that these 50 elements are having let's suppose 20 inversions with them, okay, with them. Among them, whatever is there, let's not worry about it. But they are having 20 inversions with them. Now suppose you are sorting it. Okay, suppose you're only sorting with this area. Now how many inversions will they be having again? Can you tell me? Okay, so suppose you are sorting this, then how many inversions these 50 elements will be having with them? Let me know. Even if you sort it, right, even if this is sorted, then also there will be 20 inversions, isn't it? So basically, earlier if there are 20 inversions, and then whatever change you make here, the 20 inversions with them will still be persisting, right? Okay, so I hope you are understanding this, that these inversions we don't need to worry about it. We can only increase or decrease the inversions among them, right? Among the subarray, among the subarray wherever we are making any change. Okay, among the subarray only, right? Among the subarray only. Now I am saying that maximum you can maximum the change that you can make is basically 9 inversions. Why? Maybe this 100 is inverted with all, this 50 is inverted with all, right? Then if you are swapping them, then these inversions will be decreased by 9. Okay, and earlier whatever was the inversions, that will be remain same. Okay, that will remain same. Okay, understood? Great. Now let's see this question. This was extremely nice question. Okay, this was extremely nice question. How many of you were able to solve this? They are saying that you want to find out the log n elements, okay, such that largest element, second largest, fourth largest, eighth largest, and so on, right? And then they are saying they consider that we have the algorithm. We already have, let's suppose, the algorithm. Okay, we already have the algorithm which is saying, okay, which is saying that kth largest element, that you can find the kth largest in theta of n, okay, of array of size n. In array of size n, you can find the any largest in theta of n. Now suppose that you want to find out first largest. How much time you will be taking for the first largest? N time. For the second largest, how much time you will be taking? Tell me. For the second largest, again n time. For the third largest, again n time. Sorry, not the third largest, fourth largest, again n time. So basically you can keep on taking n time. There is no problem, and these are the log n elements. So definitely n log n time, in n log n time you can definitely do it. But this is not the best, right? This is not the best. What is the best thing that you can do? See, in n log n time you can definitely find out all of these log n elements as per the question. But this is not the best thing that we can do. There is something even better we can do. Can you tell me? Okay, this is basically, this question is a small version of they have been asked already in TIFR. Okay, I will put the link later on. So in TIFR they have asked the question, and this question is basically the small version of that question. Okay, I will put the TIFR link in the description, okay, or in the pinned comment. So see, this is very interesting question. See here, that you need to find out first largest, second largest, fourth largest, and so on, right? And n by 2 largest. Let's just first find out n by 2 largest, n by 2th largest. How much time it will take? Order of n, isn't it? Now once you find out n by 2 largest, wherever it is, okay, wherever it is, I will do one thing. Do you remember the pivot operation in the quick sort? It basically says that, okay, you have the pivot here. Before this lesser than pivot, after this greater than pivot, isn't it? So basically, I will use the almost same method. The first step is that I will find the n by 2 largest first. Okay, instead of finding the first largest first, I will find the n by 2 largest first. So this is the step one. Step one, find n by 2th largest. Tell me how much time you will be taking to find n by 2th largest? Order of n, because you can find kth largest in order of n. That is given in the question. Now, as a step 2, what will I do? I will rearrange elements such that n by 2th largest is on its correct position. Okay, how much time this will be taking? Just order of n. I can definitely use something like pivot method, right? Okay, and I can definitely rearrange such that the n by 2 largest will be on the correct position. So basically the whole process is just taking n by 2. Oh, sorry, n time. So what I'm trying to say, that you will be finding n by 2th largest, right? You will be finding n by 2th largest, and then you will be putting the n by 2th largest at this correct position. So basically it will take order of n, right? For the n by 2th largest finding and to put it in the correct position, it will take order of n or theta of n, you can say. Now tell me the n by 4th largest or the next largest will be where? Okay, let's suppose this is the n by 2 largest. Obviously it will not be in this position, this area. It will be on this area only, isn't it? Let me know if that is clear, because that is very crucial to understand in this particular question, that the n by fourth largest will be in this area only. Okay, it will not be in this area, right? So since the n by fourth largest will be in this area, so what you can say, that now if you want to find out the n by fourth largest, okay, now you tell me, that how much time you will be taking. Will you be finding n by fourth largest in whole array or just n by 2 array? Just in n by 2, right? In this n by 2 array. So you will be taking n by 2 time, isn't it? See, to find out the n by 2th largest, okay, to find out the n by 2th largest, we have taken n time, that I agree. We have taken n time. But now to find out the n by 4th largest, we will be taking n by 2 time. Now wherever is the n by 4th largest, right? This is. Now if you want to find out n by 8th largest, you will be finding here, right? So again it will be taking n by 4 time only. So initially you have taken n time, then n by 2 time, then n by 4 time, and so on, right? And since it is a decreasing GP, so you can definitely ignore all of this. So this is order of n or theta of n is the answer. Isn't it a very nice and beautiful question? Let me know if you have understood this question completely. See, what I'm trying to say here is that if you want to find out the kth largest, it is given that you can find out in theta of n, right? It is given in the question. Okay. And these are the unsorted array of n distinct elements. Okay. Yeah, array is unsorted. So see, obviously if it is sorted, so if it is sorted, then why you will be taking so much time, right? See, you will find out n by 2th largest, and then you will put it in the correct position, and then you will say, now let me find out the n by 4th largest in this remaining half only. That is the trick here. So initially you will be taking, I agree, you will be taking how much time? Initially you will be taking n time, then n by 2 time, because the array size is half, now n by 4 time, and so on, right? Now n by 4 time and so on. So ultimately you will be just taking theta of n time to find all of these numbers. Okay. No, how it can be on the right side? If you have repositioned it, okay, that will just take, see, the repositioning will just take, rearrange will just take n by n time, right? So you find out wherever is the n by 2 largest, doesn't matter. Then you will, just like a quick sort pivot, you will be repositioning it, this n by 2 largest, in this correct position, and this rearrange will again take just order of n. Okay, this rearrange will again take just order of n. So ultimately this is just order of n, 2 times order of n, but that's fine. That's order of n only. I'm rearranging, right? Now if I want to find out the next largest, n by 4th largest, that will be on this half only. That will be in this half only. Okay. So that is why you will be taking n by 2 time only next time, and then so on. Then you will rearrange and n by 4th largest wherever it is. Now the next time you will finding the next largest in this sub array only. Okay, you are keep on dividing the array. That's why in the question also I've said it. Okay, hint. Similar to binary search, but we never have to worry about one of the binary search. We never have to worry about one of the sub array. Okay, I have also given the hint that, okay, something like that. Okay, we never have to worry about one of the sub array, just like in binary search. Let me know if you have understood this question completely, and you are appreciating the question. This is a very, very nice question. Okay. See here that now we will find the n by 4th largest, but here is a good news. You don't need to check all the n elements. You can just check the subarray left of the median, which are n by 2 elements only. So now again there will be just n by 2 n by 2 elements to search for. Okay. So you are dividing your subarray into 2 half in theta of n. You can say in theta of n work, then you will say that, okay, now my problem is of n by 2. Understood? Okay. So now let's just solve this question. This question also is very nice question. Okay. This question is also very nice question. How many of you were able to solve this question correctly in the exam? So what this question is saying, consider a directed graph G which has a source vertex S and a destination T. Okay, so they are saying you have S and T, right? Yeah, if array is sorted, then we will just take log n time. Yes, that's nice observation, because you just need to basically pick the elements. You just need to enumerate it. Okay, I mean, you don't need to actually do any work in finding. You just need to, you can say, enumerate it. Okay, you just need to print it. Okay, or just need to give the elements. I mean, the question, whatever the question says, if you need to print it, you can just take log n time, right? Okay, let's just see this question. What they are saying: consider graph G with a source vertex S and a destination T, and a non-negative edge length, right? Non-negative edge length. So, under what condition is the shortest ST path? ST path. Okay, under what condition they are saying shortest path ST will be guaranteed to be unique? When all edge lengths are distinct positive integers? No. Okay, it doesn't guarantee to be unique. Let's suppose it is 1, it is 2. So there are two shortest paths, even though all of them are positive integers and so on, right? Okay. So that's why this particular option is false, right? I mean, this is false. When all the length are distinct positive integers and the graph G contains no directed cycle, yeah, it doesn't contain any cycle, and these are distinct positive integers, is this unique between S to T? No, this is not unique, right? So that's why this is also false. I mean, this is a counter example for A and B both, right? This is a counter example for A and B. Okay, this is a counter example for A and B. Now let's just see the option C, which is the most interesting option, and that's what makes this question very beautiful question. So what they are saying, when all edge lengths are of distinct power 2. So suppose this is S, this is T, and then let's suppose they are saying that in what condition that S to T path will be, shortest path will be unique. Let's suppose this is the shortest path, right? Now see, let's suppose this is 2 power x, this is 2 power y, this is 2 power z. Okay, I mean, if everyone is in 2 power, this is 2 power x, this is 2 power y, this is 2 power z, and so on, right? If everyone is in 2 power, can you ever make this 2 power x plus 2 power y? Is this possible if everything is different? Everything is distinct. Okay, distinct power of 2. Okay, so which means 2 power x plus 2 power y, is this even possible for any value of x, y, z, distinct values of x, y, z? The answer is no. Why that is the case? See here, 2 power x will be 1 followed by x zeros, right? I mean, if you want to understand with the binary, 2 power y will be 1 followed by y zeros, right? 2 power z will be something else, maybe 1 followed by z zeros. So even if you add these two, 2 power x and y, can you ever get one only at one place? No, right? You will be getting one at multiple places. And in 2 power z, that is only on one place. In 2 power z, that one is only on one place, right? So basically, whatever you do, you can't get this 2 power x and 2 power y as 2 power z. Okay, and then you can even extend this, that 2 power z plus 2 power p or something. So basically, never two distinct power of, or maybe multiple distinct power of power of 2 cannot be sum up different distinct power of 2. Okay, you can try to understand this using binary. So basically, if everyone is in power of 2, then it is definitely possible to get the unique shortest path. I mean, you will not be having multiple shortest path. Multiple shortest path means that 2 power x plus 2 power y is definitely equal to 2 power z plus 2 power or maybe 2 power p plus 2 power q. Okay, here you will be having 1 at p and q, here you will be having 1 at x and y, right? So basically this is s, this is t, and then let's suppose these are the two paths. Okay, having different number of, having basically multiple nodes, and now I'm claiming that some of these two paths cannot be same. Okay, let's suppose it is involving, for example, it is involving 2 power x and 2 power y, it is involving 2 power p and 2 power q. Since none of this is same, okay, x, y, p, q, none of this is same, So that is why this summation will be 2 power x plus 2 power y, which means in binary 1 at xth and byth position, right? Here 1 is at pth and qth position. How the summation could be same? How the summation could be same, right? Understood? So the summation cannot be same. Hope you understood that if we are having everything in 2 power, then two paths cannot have the same summation. So that's why the shortest path will be unique. That was one of the very nice question here. Okay, see, because of this option C, and then you can understand this using binary. Okay, so hence you can say C is the correct answer. Let me know how many of you really understood this solution. How many of you have really understood this solution? Okay, great. Now let's just solve this particular question, which is also a good question, and it's a similar kind of question. I think we have already given in one of the weekly quiz or maybe test. I don't remember, but yeah, weekly quiz or in the test series, the similar kind of question is there, right? Okay, the similar kind of question. Now let's just solve this question. Okay, great. So Amit, Nandini, these people, Sanchit, Junaid, these people have already solved this question correctly. I'm very happy to see that you guys have done this question correctly. I mean, I was assuming that this question is very nice. I mean, it was one of my favorite question, you can say. Okay, because of this binary interpretation. Okay, because of this binary interpretation, it got corrected. It got hit into my mind that okay, this is going to be one of the very nice question. So really very nice to see that you people have attempted this correctly. Now, let's just see this question, what they're saying. Suppose that last operation you perform in the binary heap was inserting the key x. Okay. What are the possible values of x? So tell me, how many of you were able to solve this question? How many of you were able to solve this question? Okay, great. So this question was basically an inspiration from this particular question which has already been asked in GATE. Let me tell you how these questions are related. Let me just tell you. Suppose you add, okay, suppose this 11 was not there, okay, or some element was not there. Then let me just take this on the next page and let me tell you that how to solve the question, right? Suppose this 11 is not there. Okay, or maybe this is 11 and then or maybe you can say, okay, maybe I can draw this because it will not look very nice here. Okay, let me just draw this. This is 20. Let's suppose this is 13, this is 19, this is 15, this is 1, this is, let's suppose, 10, this is 10, this is suppose 11, this is 8, this is 5, this is 9, and let's suppose you are inserting some element which is 18. Okay, suppose you are inserting 18. Now what you will do to insert this 18? Suppose you are inserting 18, which will get inserted here, right? Initially this is heap, right? So it will get inserted here. Now this 18, since it is a max heap, then you will say that okay, whoever is the maximum between 18 and 11, you will swap these two. Right? Whoever is the maximum between 18 and 11. So you will swap this 18 and 11, and then you will say that okay, now after swapping this 18 and 11, 18 will come here and 11 will go here, isn't it? 11 will go here. Now you will say that okay, this 18 and 13, right? Now you will be again checking between 18 and 13, and then you will say that okay, this 18 is greater, so you will swap this also with the 13. So 13 is here, and then this is 18, isn't it? So now you will check, okay, this 18 is smaller, so you will keep it here as it is. So which means, let me just tell you that what is happening here, that you will say that, see, that, okay, that you have started with this, right? You have started with this, and ultimately you are getting this. Okay. So which means, let's suppose if you want to insert 18, then 18 has got inserted here, and you see here this path, right? Path from root to leaf. Only this path is getting changed. Okay. So 18 will get inserted here, 13 is shifting down, and 11 is again shifting down. 18, 13, and 11. This relative ordering is same. So basically what I'm trying to say, can you, I don't have the animation here, but can you understand the animation? That just imagine that कि 18 उड़ता हुआ आ रहा है, 13 यहाँ शिफ्ट हो गया, और 11 यहाँ शिफ्ट हो गया, और 18 यहाँ पे आ गया. Can you just think about that animation? I will put the animation later on. Like I don't have the animation currently, but 18 ऐसे आ रहा है, 13 just नीचे, 11 just नीचे. So basically this is along the path only. Along the path only you are making this change, right? Along this path only. So basically this if you are inserting whatever element you are inserting, basically it will get changed from the newly inserted leaf to the root. I mean along this path only. The only change will be along this only. Okay. This thing will remain intact. This thing will remain intact. This thing will remain intact. This also element will remain intact. Okay. So the only changes that we are making is basically along this path only. Is this understood to everyone or not? Let me know. Suppose the 18 is bigger than this, then 18 will shift even further, right? Is this understood to everyone? Okay. Now see here that see, isn't it always sorted? Because this is a max or min heap, whatever heap it is, this is greater than this is greater than this. Isn't it always sorted? Isn't this path is always sorted? Let me know. Is there any confusion in this, that this path may not be sorted, this particular path, isn't this particular path is always sorted? Yes, right? This path is always sorted. So since this path is always sorted, hence you can say that if I'm going to insert this 18 in this path, somehow, maybe if can I use a binary search along this path only to find out that where will 18 come? 18 is just smaller than this and greater than all of this, right? So basically this question, see here, this question that has been asked already in GATE 2007. So what they're saying, consider the process of inserting an element to the max heap, where the max heap is represented as an array. Suppose we perform a binary search on the path from new leaf to the root to find the position of newly inserted element. See, my idea is not to solve this question, okay? But the idea is to tell you that, see here, that why this line makes sense, okay? Why this line makes sense. Tell me, how this binary search from path to new leaf to the root is making any sense? Have you understood that this line makes completely sense, that from root to newly inserted leaf, if you do the binary search, then also you can find out the position, isn't it? So I'm sure that most of the aspirants, even almost 100% of the aspirants, all the aspirants, I can say almost 100% of the aspirants have not paid attention to this line, that why this line is even making sense. They might have said that, okay, maybe the log n is answer or whatever. I mean, log n is answer or whatever, right? Because the log n elements are there from path to leaf, and if you are doing a binary search, maybe the log n is answer. Okay, maybe you can say the b is answer or something. So my intention is not to solve this question. Maybe whatever is the answer, okay, b is answer, b is not the answer. It doesn't matter for me. I just want you to notice that, see here, that this binary search is making a complete sense, right? No, it's not making just because it is sorted. It is making sense because this element will be basically in one of this position, right? The element 18 will be in just one of this position. That's why it is making sense. See, will this make sense? That okay, let's just find out the among this path, the binary search among this path. Will this make sense? This is also sorted. See, this is also sorted, isn't it? But are we doing binary search here? No, We are basically doing binary search here because only this particular thing is, this particular path will get impacted and nobody else will get impacted. And using binary search, I can say that okay, if 18 is at this position, I can just shift everything down right away, right? See, just because this is sorted, it is not the case that okay, this line is making sense. It is making sense because I know that once I find the position of 18, then I can definitely shift everything just down, right away. Okay, so you can say that this particular line makes completely sense, completely sense. See, even if you see the best answer selected, let's just see if they have written the significance of the line that is given. So number of elements in the past to row is log n and all the elements are sorted, okay, and log n. Since a heap is a complete binary heap in the array implementation, we know. No, see, they have also not written the significance of the line. The significance of the line is important. How many of you have really understood that why this particular line makes sense? Why this is making sense is because we know that once we find out the position along this path, okay, along this path, if we find out the position, then we can definitely plug in and then we can say that okay, all the elements are just shifting down, okay, just like animated, okay, वो एकदम से नीचे आ जाएंगे, just like a flow. It's just like a flow, okay, they will just flow down the path, okay. So whatever is the path, they will just use this. Let me know if you have understood this completely. Okay, now coming to this question, what they're saying, coming to this question. So in this question they are saying, let's suppose the newly inserted key, it just, I mean, some key we have newly inserted, so what key might have been possible, right? What key might have been possible? Is this 11? Yes, 11 is definitely possible. So basically see, in this question, okay, maybe I can draw the diagram again. So in this question, they are saying that you have here, you have 18. So let me draw the diagram. So this was 18, this was 13, right? Okay. So see here, this was 18, this was 13, and this was 11. Okay. Now, as you know that only whatever got inserted is either 11 or 13 or 18 or 20, isn't it? Can it be 8? The newly inserted, can it be 8? See, the only change that you make is along this path only. Okay, along this path only you make the changes. So it might be 11. Definitely 11 is possible. Maybe the earlier, before 11, the earlier you can say that the heap will look like this, right? Before 11, and then you might have inserted 11. You might have inserted 13 also. Why? Because before 13, maybe it was looking like this, and then you might have inserted 13, right? You might have inserted 13. So 13 will get exchanged here, and then you will say that okay, that's why the 13 is also a legit option. Okay, maybe 13, maybe 11. Is it possible that you might have inserted 18? Yes, maybe before 18 it might have looked like this, right? See, before 18 it might have looked like this. This was 13, this is 11. Maybe you have inserted 18, and before 18 you might have it might have looked like this. Now you will swap it, right? So 18 is also a legit option, right? Maybe 11, maybe 13, maybe 18. Okay, so basically 18 is also a legit option because before 18 it might have looked like this. Now actually the heap that is given to you is like this. Let me write it again. 18 was there, 13 was there, and this was 11, right? Okay, so this 11 is definitely the legit option. 13 is definitely a legit option, which means you can say that 13, because of if 13 was not there, then that it might have looked like this. See, if 13 was not there, then it might have looked like this. So basically you just remove 13 and see, like it might have, what might have been the previous position, right? 18 is also a legit option, but is this 20 a legit option? If 20 is not there, then the tree must have been, okay, or the heap must have been something like this. If 20 was not there, then heap must have been something like this. You will say I'm going to insert this 20. See, this should be intact, this should be intact, all of this should be intact, or only the thing that you might have changed is this only, right? This must be 18. Okay, this must be 18. This is 13, this is 11. Is this possible that you are now inserting 20? Is this even the heap? Is this even the heap? Tell me. So is this heap? This is not the heap, right? This is not the heap. Since this is not the heap, so that's why this 20 is not possible. Okay, because if you are inserting 20, then the heap, earlier heap was not this, it was something different, right? 19 might be here, 18 might be here. Okay, see, if you're really inserting 20, then the earlier heap might have been like this. Let me just draw the earlier heap. Okay, if you're really inserting 20, then earlier heap could have been like this. To just insert this 20, you can say the earlier heap might have been like this. This must be 19, okay, and this must be 18. And now you can insert 20. Yeah, now you can insert 20. This must be 19, this must be 18. Now you can insert 20, okay? Now if you insert 20, then this path will change. So basically with the given heap, 18 is, since 18 is here, so that's why with the given heap the 20 is not definitely the newly inserted node, right? If 20 is the newly inserted node, then the earlier position, okay, in the earlier position to start with, this is not even the heap. Understood? Okay, so hence all of this in this path, whatever is this 11, 13, 18 was possible, but 20 was not possible. Okay, 20 was not possible. So hence, what is the answer? 20 is not possible, 13 and 11 is possible. This is 8, not 18. Okay, so some people mark it, they thought that this is 18, this is 8. Okay, don't do in the hurry. So C and D are the answers here. Understood? Okay. See, if you understood this question, just let us know in the comment that the very first time you might have understood that why this line is even making sense. See, they have got 18,000 views on this question, and it is very surprising to see that none of the aspirant has commented that why this line is making sense. Okay, if you have understood now that why this line is making sense, then let us know in the comments. Okay, you can comment later on. Is this particular recursion is okay to everyone? Linked list recursion. So they are saying that you have 1, 2, 2, 8, 6, 2, 2. You have 1, 2, 2, 8, 6, 2, 2, right? Okay, and then this is basically finally pointing to null, right? Finally it is pointing to null. Now they are saying that there is some function which is doing something like this, right? Which is doing something like this, and you are calling this function with 2, right? So I think this is approachable question only. Let me just tell you that how to solve this question, right? See what they are saying, that here if the value is x, see, initially you will be calling with this. Initially whenever you are calling for the head is a local variable here, right? Head is a local variable here. Head is initially pointing to 1. Okay, then they will say head value is x, which is not true. Then you will go to else, and then you will say head next equal to, which means head next is basically this pointer. Now you are saying head next is equal to, this pointer is now pointing to whatever the next function call return. What does this mean? We have already done in the class these kind of recursions. So basically you will say that this head next, okay, it is in the suspense state. You will say, okay, this will point to whatever this function will return, the next function is returning. So currently it is not pointing to anyone. Currently you can say it is not pointing to anyone. It will point to later on. I mean, it will point to whatever the mystery of this will return, right? I mean, this head next will point to whatever this particular thing will return. Now you are calling this mystery with head next, which means head next is pointed to this. So this is a different call. This is a different recursive call which I am making. See, this is a different call which I have not got returned. See, this head next, here there is a local variable head, and head next is waiting that okay, whatever you return me, I will point it, right? Whatever you return me. Now here again there is a pointer head, which is a local variable which is pointing to 2, right? Now since the value is x, you will say that okay, head next temp you are storing in the head next, and then you will free this up. You will free this up, and temp is basically pointing to head next, whatever head next temp is pointing here, then you will return temp, okay, which means you will return a pointer to this. Now it was waiting, this was waiting to the case that whatever you return me, and it is returning the pointer to temp, so it will start pointing to this too. See, this particular function, after this if, it will say that okay, I am returning a pointer to this 2, and this is waiting, right? This is call is now gone, and this is waiting that whatever you return me, and since you are returning a pointer to 2, so that's why I will start pointing here. So that's why it is 1 2 8, I mean this 2 will get deleted, 1 2 8 6 2 2. Okay, understood? So basically we have done the linked list recursion. How many of you are Go classes student? We have specifically done this linked list recursion very nicely to make sure that you understand that how the recursion work in the linked list, because most of the students just by heart it, okay, they do not clearly understand the linked list recursion. Okay, let me know how many of you were able to solve this particular question. How many of you were able to solve this particular question? So they're saying what will the content of the stack of SLR parser immediately after shifting the last character of the string A star B. So what you need to make? You need to make the SLR states, and then you need to check that how to solve this question, right? A star B and then open parenthesis. Okay. So let's just see this. See, this is, let's suppose you are augmenting it. Maybe you can augment with A prime, and then you need to make the states, right? Dot B plus A, and B will give dot CB dot C will give dot D star dot D will give dot A dot A or B. Okay, something like this. And now if A is coming, so I'm not making all the states. Let's just say that if A is coming, then what will happen? If A is coming, if small A is coming, then you will go to D gives A dot, right? Okay. Then have you seen the rerun of DFA? Rerun of DFA. Have you seen that particular video? Let me know the rerun of DFA. Have you seen that particular video? Rerun. How many of you have seen rerun of DFA LR0 Go classes? If you just just Google this, then you will be getting. Okay, I mean Google in the sense if you just use a YouTube, then you will be getting that video. Let me just put that. Okay, let me just put that video here itself. Okay, what do I mean by that? So if you have seen that rerun of DFA, yeah, most of you have seen, right? So if you have seen that particular video, which is rerun of DFA, right? This particular video, then you should have, or you should have easily able to solve that question, right? You should have easily able to solve this question. This is a rerun of DFA, really understanding the LR0 automaton. Okay, using the rerun of DFA. This is very important, very important. I can say very important video. Okay, important video to understand the parsing. Okay, to understand parsing. Just Google this out, and then I mean on the YouTube there is a video. Just see that video. Okay. Okay. Just see that video. So basically, like I'm not going to solve this question because it will unnecessarily take 5 or 10 minutes, and then until and unless you watch this video, then you won't be able to understand the solution also. So if you watch it, then you know the answer directly, right? How many of you want me to solve this question now? Those people who have watched it, just tell me how many of you want me to solve this rerun of DFA? Those people who have already watched. Okay. So if you watched it, then you should be able to solve the question. You just need to rerun the DFA again and again, and then you will be easily able to solve this question, right? Okay, it is easy question and should be doable. Right? Now let's see this question. This question is very interesting question. Let's see this question. What this question is saying, suppose this is a router, okay? This is a router which is given to us. Now in this case, if this is a router, then these are the, let's suppose, two subnets, right? As we know that, okay, every interface of the router is one subnet. So they have given this 31 is basically 3 times 0 and 5 times 1. 28 is, I think, 3 times 0, and then this is 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 16, and then 8. This will be 24 and 28. Okay, so 28 is this, right? This is basically 28. So 28 is, you can say, 3 times 0 and 1 1 1 0 0, right? This is 28. Okay, so please watch this video. Okay, if you have not watched that, then please watch this video. Okay, for this question, for this particular question, please watch this video. This is very, very, very important video, I will say. Okay, and then if you understood, okay, after watching this video, if you understood, then please let us know in the comment. So here they are saying that if you want to use a mask, then which mask you will be using? See, can you say that till this point, since everything is matching, right? Till this point everything is matching, then can you say that answer should be, the longest prefix match should be 135.126.11.28 slash this is already 24 bits slash 5 6 7 8 9 10, so slash 30. Should this be the answer? Okay, should this be the answer? Slash 30, let me know. Is this slash 30, is this a correct answer? No, right? The slash 30 is not the correct answer. Why? Let me just tell you. See, if you put the slash 30, interestingly, if you put the slash 30, then what will happen? Let me just tell you. See, if you put the slash 30, then what will happen? Then you will say that, see, if you are saying that, okay, till this point you are saying, let's suppose you are saying till this point, you are giving that to a network administrator. It's saying that, okay, this is basically the subnet mask, which means you are saying that your subnet mask will be this one, right? 0 0 0 1 1 1, and then you can change this. So if you are giving slash 30, can you tell me what is the network mask? I mean the broadcast address. Sorry, what is the broadcast address? So if you use slash 30, then the broadcast address, see, 135, if your subnet mask is this 135.126.11.28, right? Then if you use, let's suppose, if you use slash 30, okay, slash 30, then what is the network address, and what is the broadcast address? So the network address will be 135.126.11, and 28 is nothing but 0 0 0 1 1 1, and then basically you can change these two bits, right? You can change these two bits. So this is 0 0 0 1 1 1, and then if you change these two bits, then it will be 0 0, it will be 1 1, 0 0 for the network address, and 1 1 is the broadcast address. So basically for this particular network, the broadcast address is having this all the ones, right? But they are saying that it is already given to one of the interface. All the ones is already given to one of the interface, right? So that is why you cannot assign this slash 30. See, why you can't assign this slash 30 is because this is given to you, and then this 31 will be 1 1 1 1 1, and then these are the 3 zeros. This 28 will be 0 0 0 1 1, and then 3 zeros. Okay, now if you use, let's suppose, if you say that, okay, I am using 0 0 0 1 1, okay, till this point it is fixed, sorry, 1 1 1, right? I'm just changing this. If you change this, then if you are using 1 1 in this place, then if this is the broadcast address, then in that case it cannot be it cannot be the IP address of this interface. That's why you can't use a slash 30. Similarly, even if you use till this point, then also the broadcast address will be just with all the ones at the end. And this is already interface address, right? If you use till this point also, then also the broadcast address will be all the ones, and this is also same with the interface address. If you use till this point, then also the broadcast address is basically conflicting with this particular 31, right? That's why you have to use till this point only. And then if you use till this point, then this is 26 bits, right? And then the broadcast address will be all the ones, then all the ones, right? It is not having the conflict with 31. Okay. So till 26 only you can use. This was very, very nice question. How many of you were able to do that question? This is something that we have already seen in the class, right? I mean, there was some weekly quiz question using which we have seen this particular concept. So that's why A is the correct answer here. Till 26 only you can give, because otherwise it will be conflicting with every of this. If you use this, then broadcast address of this particular network will conflict with this particular interface ID. Okay, any of this you will do, it will be a problem. Okay, great. Now let's see this question. This is a token bucket question, right? This is a token bucket question that was there in the quiz, in the exam, in the mock test. So this was a token bucket question. How many of you, by the way, have seen goclasses token bucket video? That is already there with the 1.8k views, leaky bucket and token bucket on YouTube. Can you search on YouTube? Okay, can you search on YouTube the token bucket video? So in this particular video, I have solved GATE questions, GATE 2008 question and GATE 2016 questions. So I have solved 2 GATE questions with very nice explanation. And even in that video, let me just tell you, there were comments like this, that okay, the geometry, I have told very nice method to solve these kind of questions. Okay, so just watch the token bucket video, and even the toppers like this Palash, okay, this Palash Behra. So he was AIR 68 in GATE 2023. Okay, he has commented on this video. Thanks for the video. I almost skipped this topic. Okay, so basically, just watch this video. I have solved 2 GATE PYQs here, 2 GATE PYQs, right? And multiple comments I have got, including AIR 68 Palash has commented that it is a really nice video, and actually it is a really nice video. So just see this particular video. Okay, this is not a very long video, just half an hour video. Just half an hour video. In this half an hour you can just cover this concept. Okay, just half an hour video. Cool. So this is related to token bucket. Let me just solve this question, but I will strongly recommend, to particularly understand this topic, you should be watching that particular video, right? So what they are saying, that 30 MB of data is there that you want to inject. So this is host, right? That 30 MB of the data, 30 MB that you want to inject, and this is token bucket, right? Now the token bucket has a capacity of 15 MB. So already it is having 15 MB, and the token is getting filled with the 5 MB. Okay, 5 Mbps. Data is buffered. How long is to take 30 MB? Okay, assuming that this out bandwidth is 20 Mbps. This is the setup that you have, right? Okay, this is the setup that you have. So to send the 30 MB, how long you will be taking? That's the question, right? So see here, easy question only. In 1 second, you can actually send this 20 Mbps and also whatever 5 Mbps that is coming in, which means you can say this 5 Mbps and this is, I mean, you can say it is directly connected, which means 5 Mbps, what I mean to say, let's suppose this is a 20 Mbps pipe. Okay, 20 Mbps pipe. And you already have some data to send, and let's suppose you are directly connecting whatever you are getting, you are directly injecting this. This is anyway directly connected to one pipe which is of 5 Mbps, right? Now Now, this is, I mean, the remaining is only 15 Mbps basically, or only the 15 Mbps you can understand like this, that okay, this 15 MB you can send in 1 second, right? And whatever the 5 Mbps is coming, then that you can definitely send. So what I mean to say, in 1 second you can send, in the first second you can send 20 MB of the data, right? The complete bandwidth you can use. Okay, see, in 1 second, the initial second, you can send 20 MB of the data, 20 MB, the complete bandwidth, which is of 20 Mbps, you can definitely use that complete bandwidth. Okay, why? Because 15 MB that you already have and 5 Mbps that you will be getting in 1 second. So this is 20 you can definitely use in 1 second. But from the next second, this will get empty from the next second. Okay, in the second, you can just send 5 Mbps, right? Because there is nothing buffered, right? You can send 5 Mbps. So 5 MB of data, total 25 you have sent till now. And then in the last second that you can say, in the last second, which is third second, right? Which is the third second. In the last second, you send 5 MB more. So total 30 MB you can send in 3 seconds, right? So in 3 seconds you can send. I have solved very nice questions, have shared very nice strategies to solve these kind of questions in this particular video. Okay, just watch this video. This is a small video, half an hour video. Okay, and has got many appreciations. So why not just spend half an hour and make sure that if this kind of question is coming, that you can definitely do. And just put a comment. Okay, just put a comment whenever you watch this video. Just let me also know that you have watched, so that I get to know that okay, you have really watched this video, right? So I think this is all the questions from my side, which means that all the questions which were required, we have solved. So let me just quickly tell you that the questions that we have solved, including the part 1 and part 2, were like this, right? So this question, the third question, and then this page table entry question, which was really a good question. This page table entry question, and then I think, yeah, this foo question, right, which was related to compilation. This was easy question. This was also a conceptual question which were related to signed and unsigned things, right? And then yeah, this is over. And then merge sort, I think this was the easy question only. This was also the easy question. This one more questions were really easy according to me, right? This was the easy question. Yeah, I will attach the PDF. Don't worry, I will attach the PDF. This was also a nice question we have solved. Okay, this was a nice question. And then yeah, this was also a nice question, easy. It was a little tricky actually. It was a tricky question, I can say. It was a little tricky to understand. Maybe at the first go you might have not understood this. Okay, and then this was easy question, right? This was easy question. We have solved it. This was also a really nice and easy question. Okay. Yeah, for the token bucket, that is the only video we have on the YouTube. Okay, and yeah, this is also related to eigenvalues. Okay, this was really a nice question. And then we have solved many such questions. For example, particularly this cache question is also very nice, right? Do you remember this cache question we have solved yesterday? This was also very nice question, this cache question, right? So these are the two approaches of the cache. Now this question also really good question. This question really good question. And what else? This question related to the linked list that we have solved today is nice question, related to race conditions and all, right? Okay, this round robin question telling you that how to use the queues. Okay, this was really a good question, understanding that how to use the queues, right? And then what else? Then this particular question was related to the pointers, which was I think really nice. And then we are using the dynamic programming in this question, which made this question really nice, right? The dynamic use of the dynamic programming for this particular question. Okay, this the related to inversion, right? Related to inversion, that how the inversion is working. This was really a good question. And yeah, this was extremely nice question, that how to do in order of n, okay, or the theta of n. This was really a very nice question. Okay, and then because of this binary, okay, this there's all edge lengths are distinct power of 2. Because of this, this question was really good, because of this particular line. Okay, and then if you remember that heap question went really good, because we got to understand this particular gate to them 7 question, because of that heap question, right? Why this particular line is making any sense. Okay, And then the linked list question, this was easy question, I think. This, for this particular question, you need to watch the video if you have not watched, otherwise you could have solved this question easily in the class. Yeah, this was also really nice question, that how the network administrator is deciding. And the token bucket question, you can see that particular video of half an hour, and there has been two PYQs I have solved, multiple comments we have got of the toppers also. Okay, so I hope it was a great session. Just let me know in the comment right after the video, right after this session end. Let me know in the comment. Okay, I will put the PDF. Okay, after your comments. Okay, just let us know in the comments that how was the session. Okay, how was the session? Have you learned new things in these sessions, in these two sessions, or not? Okay, just let us know in the comments. Okay, please do a comment. Okay, please do comment, so that the other aspirants who don't really know us, they will get to know, right, that okay, there is some coaching which is actually doing some good job. Okay, so let us know in the comments, because just like you, we also need the motivation. Okay, so thank you so much, thank you everyone, take care, and let me know which question was the favorite. Okay, which question was the favorite, liked. Okay, thank you so much, thank you everyone, take care, bye bye.